Hi everyone, my name's Dominique, and I'll be talking to you today about my project focused on highly organized polymer nanoyarns for suture materials. First, some background on nanofibers. These are fibers with diameters ranging in nanometer range. They have large surface area to volume ratio, making them really suitable for surface functionalization compared to their microfiber counterparts. They mimic the structure of the extracellular matrix fibrils, which allows for better cellular interaction, and they can or have been shown to modulate the immune response by polarizing macrophages from M1 to M2, which is pro-healing, and it leads to improved healing outcomes. We're particularly interested in nanoyarns, which are bundles of nanofibers. As a bundle, they have better mechanics than the fibers on their own, yet they still maintain this bioactivity because they're composed of these nanofibers with a high surface area to volume ratio. So we think these are a really interesting material for sutures, given that they can meet some of the current limitations due to the surface functionalization capability. Some of our aims of this project were to compare the mechanical and functional performance of nanoyarns with monofilament counterparts in a commercial suture to determine the feasibility of incorporating endolysidine directly into an electrospinning solution for fabrication of antimicrobial nanoyarns, and to evaluate how changing the ratio of PEG dimethacrylate to PCl affects the mechanics of a nanoyarn. So onto our methods, we made quite a few different electrospinning solutions with PCl, so just pure PCl, pure PLA, and then we had a PCl and peptide or endolysidine of varying concentrations, and then PCl and pegma blends. We electrospun all of these onto our custom parallel track system, which allows for post-rolling capabilities and deposition of aligned fibers onto a roll-to-roll collector to allow us to create these long sheets of nanofibers as shown in letter B. This system is pretty unique given that most nanoyarn fabrication systems do not allow for post-rolling capabilities, have limited control over alignment, and have limited length capabilities. After we create our nanofiber sheet, we put this onto a custom yarn spinner where we control uptake and twist to have a resultant twist per inch of 5. And then we are left with a bobbin of nanoyarn. For aim 1, we did testing on the PCL, PLA, commercial suture, and monofilament counterparts of PCL and PLA. We've done imaging, tensile testing according to a suture-specific protocol, degradation, knot pull, and suture pull-through. We've also done zone of inhibition for our AIM2 on the antimicrobial nanoyarns, and finally we did that tensile testing specific to sutures for the PCL and PEGMA blends. So going through our results and conclusions for AIM-1, looking at the performance, the nanoyarns were fabricated with a coefficient of variation ranging from 8 to 30%, which is in line with a lot of conventional staple yarns. As we increased our draw ratio, particularly for the PCO group, we increased young modulus, ultimate tensile strength, and tenacity. The PCL nanoyarns degraded more rapidly than the other groups. However, our nanoyarn with a draw ratio 2 remained intact for the 7-day protocol and did show mass loss and correlated loss in mechanics, whereas the DR1 group had catastrophic degradation. Functional testing showed that the nanoyarns caused less tissue damage and were less prone to untying. And then we even braided our one nanoyarn group, and this showed to have matched linear density and diameter to the commercial suture and showed similar break force as well. So we're right in the ballpark of a commercial suture here. AIM2, we were able to successfully electrospin up to 10% of endolysidine directly into the electrospinning solution. However, zone of inhibition results were pretty inconsistent, so perhaps this isn't the best fabrication method for an antimicrobial nanoyarn. From there, we moved to our PEGMA PCL blends. We were able to successfully incorporate 25% of PEGMA into these blends, and with an increased PEGMA concentration, we had a decrease in mechanics. However, there was a plateau in this effect. So overall, our nanoyarns showed improved knot security and reduced tissue damage, and when braided, nearly matched the commercial suture. We do have potential for this antimicrobial aspect, and there needs to be future in vivo and in vitro studies to assess wound healing and antimicrobial activity. Thank you, and if you have any questions, please reach out.